Hello there, Mr. Sutton bringing you the AB Calculus 415 homework solutions on advanced related rates. For number one, we've got this triangle representing a 40-foot ladder that's sliding down the wall. Long story short on this one, we want to figure out this RQ distance, the distance from the ladder from the wall on the floor, at the time when the rate of change of this is 3/4 the rate of change of this downward component on the ladder. Since we have these related rates, this is a related rates problem, so we're going to start by getting an equation that ties all of this together. So I'm going to give this RQ distance an x variable, just so I can refer to it easily, and I'll call RPY, vertical component here. My equation then, we can use Pythagorean theorem, because this is a right triangle, so x squared plus y squared equals 40 squared, or 1600. Let's go ahead and differentiate everything with respect to time now. So this will be 2x dx over dt plus 2y dy over dt equals 0. At this point on most problems, we would plug things in everywhere we could and solve for the magically one remaining variable. This problem, they didn't give us enough information to do that yet, though, so we're going to have to try a different tactic. We did find out by reading the problem that this dx over dt rate of change, when the q moving along the ground rate of change, is 3/4 the rate of change of dy over dt, at least when it's moving downwards. So we could replace dx over dt with 3/4 dy over dt. We do have to make one little adjustment, though, and that is dy over dt needs to be negative when we replace dx over dt with it. Dx over dt is a positive rate of change. This x value is increasing as the ladder slides down the wall. Dy over dt is a negative rate of change. This is a decreasing value, this y distance, as the ladder slides down the wall. So if you're swapping one out for the other, you're going to have this negative because they have opposite signs normally. All right, so that at least gets rid of one of the different unknowns. At this point, I'm just going to simplify things and see if I can get rid of some more variables, because right now we still have 3 variables. So simplifying this piece over here, we've got negative 6 over 4 rather, so negative 3 over 2x dy over dt. I'm just going to add that over to the other side. So now 2y dy over dt, 3/2 x dy over dt, these both have a dy over dt. It sure would be nice to get rid of that. I'm going to go ahead and divide both sides by dy over dt. What? Dividing by a variable, you say? Are we allowed to do that? We are if we know for a fact that we're not dividing by 0. Dy over dt, that's this rate of change here. We know this can't be 0 because if a ladder is sliding down the wall, this is going to be a negative value. So we're going to divide both sides by that. So that just leaves us with y. And I divided by 2 also, so this is going to be 3/4 x. We still don't know enough to find the value of x, but we at least have a relationship between x and y now. We have an equation with an x and a y in it. We have another equation up here with an x and a y in it. You can actually set up a system of equations and solve it. One equation is the original equation. The other is the simplified version of the derivative equation. These are 2 different pieces of information that you can play against each other. So I'm going to replace this y squared here with 3/4 x quantity squared. And just squaring all of that stuff, that's really 9/16 x squared. Combining my like terms now, I'll treat this as 16 over 16, so that'll become 25/16 x squared. Square rooting both sides, we've got 5 over 4 x equals 40. And this was a no calculator problem, so I had to keep going with my mental arithmetic here. I'm going to divide both sides by the 5 here, so that's going to give me an 8 on the right side. And then if I multiply by 4, we get x equals 32 feet. Choice E. On number 2, we've got sand being deposited into a pile with a circular base. The volume of the pile is given by this volume formula, r cubed over 3. And we want to know basically what is the rate of change of the volume of the pile. Now, they didn't give us information about the radius directly. What they did give us was the rate of change of the circumference of the base. They told us that was increasing at 5 pi feet per hour. And they told us the circumference itself. at the exact time that we're trying to find the rate of change of the volume. So rather than going ahead and implicitly differentiating this volume formula right away, we're first going to replace r with something in terms of the circumference. Because we don't know about r, but we do know about the circumference. What's the circumference of a circle? Oh yeah, c equals 2 pi r. Okay, well, if I divide both sides by 2 pi, so that I have circumference over 2 pi, I now have something that I can replace radius with. And again, the reason we're doing all these gymnastics is because we know a lot about the circumference and nothing about the radius. So let me rewrite my original formula now. This will now be c over 2 pi quantity cubed all over 3. And let's just simplify this a little bit before we differentiate. So this will be c cubed over 8 pi cubed all over 3. I'll move the 8 pi cubed downstairs though, so that's going to be 24 pi cubed down there. And at this point, there's nothing left to do except to implicitly differentiate. So on the left, we're going to have dv over dt. And on the right side here, we'll have initially 3c squared dc over dt over all this stuff. But now the 3 that I have up here in the 24, I can reduce those. So this ends up being c squared dc over dt over 8 pi cubed. At this point, there's nothing left to do except plug in what I know about the circumference and dc over dt. So this is going to be then, let's see, they said the circumference was 8 pi, so 8 pi quantity squared times 5 pi, the rate of change of the circumference. This is a no calculator problem, so let's just carry this out to the end. We've got, let's see here, 64 pi squared. And then we have a pi squared and a pi. That's going to completely cancel out this pi cubed down here. So you can already eliminate any answer choices that have a pi in them. And then 64 over 8, that's 8, times 5, that gives us a grand total of 40. So choice C. For number 3, top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what's the rate of change of the distance between the bottom of the ladder and the wall? We've got two different rates of change going on here, so this is a related rates problem. Let's draw a quick little diagram and see if we can tie it all together with an equation. So we've got a triangle, essentially, if we have a ladder sliding down a wall. It's a 25-foot ladder, and I'll call this base here x, and we'll call y the height. So now, equation that ties all this together, we can use Pythagorean theorem, x squared plus y squared equals 25 squared. I would figure out what 25 squared is, but we're going to differentiate everything with respect to time anyway for our next step, so this isn't really going to matter what this comes out to, at least not at this point. It might matter later, though. So derivative, we've got 2x dx over dt plus 2y dy over dt equals 0. And now I need to plug in for everything except for dx over dt. I want to know the rate of change of x, how fast that ladder's bottom is moving away from the wall. So x, do I know the value of x? Well, they didn't tell me the value of x. They did tell me the value of y. They said the top of the ladder was 7 feet from the ground. So I could use Pythagorean theorem, 25 squared minus 7 squared, and then square root all that. Now you might remember the 7, 24, 25 right triangle. Either way, x does come out to a value of 24. And now we've got, again, a y value of 7, dy over dt. That's how fast y is changing. They told us it was moving down the wall at a constant rate of 3 feet per minute. Since it's moving down, since this distance is decreasing, that's going to be a negative 3 that we have to plug in for dy over dt. Okay, let's simplify all this now. So this is going to be, let's see here, we've got negative 42, which we'll add to the other side. And over here we've got a 48, which we can divide the 42 by. So dx over dt then is going to be whatever this reduces to, which is going to come out to 7 over 8 feet per minute. So that's going to be choice D. For this problem, we have a railroad track and a road crossing at right angles. We have an observer standing on the road 70 meters south of the crossing and watching an eastbound train going 60 meters per second. We want to know at how many meters per second is the train moving away from the observer 4 seconds after it passes through the intersection. All right, this is a little bit complex. Let's draw a picture. So I'm going to use a triangle. Here at the vertex of the triangle, we've got this is like a railroad track here. We have a train going this way. We have an observer down here. So this is going to be 70 meters right here. And I don't know what the distances are here because, well, the train's moving, but I'm going to represent them with some variables. So let me call this one x and this one z. So x will be the rate at which the observer, the train rather, is moving east, and this z, this will be the distance between the observer and the actual train. So this x is the distance between like the perpendicular spot and where the train actually is. Okay. So we have multiple rates of change going on. We need to write an equation that kind of ties all this together and use a little implicit differentiation. So since we've got a right triangle, they said right angle here, we can use the Pythagorean theorem. We can say x squared plus 70 squared equals z squared. So that gives us our starting point. And then we can take the derivative of this whole thing with respect to time. So I've got the derivative of x squared, that'll be 2x, and because we're doing this with respect to time, x and z are both inner functions of time, so we have to do a dx dt tail using the chain rule here. Derivative of 70 squared, that's a constant, so that's just 0. Derivative of z squared, that's going to be 2z times dz over dt. Now, in terms of what we're trying to solve for, they wanted to know at how many meters per second is the train moving away from the observer. So we're looking for how this z distance is changing. That's going to be this dz dt quantity. So that means that we need to figure out the values of x, dx dt, and z in order to solve for that. Now, out of all those quantities, the only of these that we actually know is this 60 meters per second that the train's going east. This is giving us our dx dt, our rate of change of x. We still don't know what the value of x actually is at this 4 seconds instant in time, but we can figure it out. If this train is going 60 meters per second for 4 seconds, well, if we just multiply these, 4 times 60 tells us that this x distance is going to be 240 meters after 4 seconds. And if we know two sides of a right triangle, we can use Pythagorean theorem to figure out the third side. So z is just going to be the square root of 240 squared plus 70 squared, which I'm going to do on the calculator because this is actually a calculator question. So let's go to Desmos for that. And let me move this so I can see it. So we just need to do square root, SQRT, of 70 squared plus 240 squared. And that's going to come out to 250. It actually was a 7, 24, 25 right triangle, if you remember that from geometry. So 250. So we've got an x, we've got a z, we've got a dx over dt. Let's plug it all in. So we have 2 times the x value, 240, equals 2 times the z value, 250. And don't forget the dx over dt. That's the 60 that we have to plug in for that. So 2 times 250. And then this dz over dt, again, that's not changing because that's what we're trying to find. So now to solve for this, I just have to go back and divide both sides by basically 500. So let me just do all of that on the calculator. So we've got 2, let me just do a big fraction. So 2 times 240 times 60, all of that divided by 2 times 250, and that comes out to 57.6, and that'll be in meters per second. So that's going to give us answer choice A.
Number 5 is a cute little problem on a sphere here. This sphere is expanding such that the area of any circular cross-section through the center is increasing at this constant rate. At the instant when the radius of the sphere is 4 centimeters, what's the rate of change of the volume? They were nice enough to give us the volume formula. This is what we're trying to find the rate of change of. So let's go ahead and differentiate with respect to time and then see what we still need to figure out. So we'll have dv over dt equals, and multiplying by 3 here, we'll have 4 pi r squared times dr over dt. Now, if you're looking for dv over dt, you need the values of r and dr over dt. R we know. They told us it was 4. dr over dt, that's the rate of change of the radius. They did not tell us that. They told us the rate of change of the area of a circular cross-section. So what we're going to do to find dr dt is we're going to use the area formula. Area equals pi r squared. And we're going to differentiate with respect to time and see if we can solve this for the dr over dt that we need to solve this other equation. So differentiating over here, we've got dA over dt equals 2 pi r dr over dt. Now we know that the radius is 4. They also told us that dA over dt, the area change, is 2. So we've got 2 equals 2 pi times 4 dr dt. Dividing by 2, we've got 1 equals 4 pi times that stuff. So dr over dt then equals 1 over 4 pi. Not the prettiest number, but it'll actually work out very nicely when we plug it back in. You'll see, I promise. All right, plugging everything back in. dv over dt, that's what we're trying to solve for, equals 4 pi 4 squared times 1 over 4 pi. This was a calculator question, however, you don't need one. 4 pi and 1 over 4 pi cancel, so this just comes out to 16, and that's going to be centimeters cubed per second since we're trying to find rate of change of volume. Choice B. On number 6, a cup has a shape of a right circular cone. Height of the cup is 12, and the radius of the opening is 3 centimeters. So on these cups, they're shaped like cone kind of problems. This is kind of a common related rates situation. I'm going to draw a diagram. So here is my cup that has a height of 12 and a radius of 3, just doing a cross section of it here. Here's the water inside, which also is a triangular cross section. So now we have water being poured in this cup at a constant rate of 2 centimeters cubed per second. We want to know the rate at which the water is rising when the water level is 5 centimeters. So essentially we have the rate of change of the volume, and they gave us the volume formula here, and they want us to find out the rate of change of the height. If I just go ahead and differentiate with respect to time for this whole thing, so I'll have a dv over dt, but on the right side, I'm going to have dr over dt and dh over dt. I'm going to have to use product rule too, which doesn't sound like a whole lot of fun here. So to make my life a little easier, since I'm looking for dh over dt, the rate of change of the height, I want to see if there's a way to express these r's as h's and just have only one variable on the right side. How can I relate r and h together? The key on this is realizing that you've got two similar triangles here. So we know that the height of the water level and the radius of the water level, because these triangles are similar, the height and the radius of the water will have the same proportions as the height and the radius of the cup itself. It's being forced into this proportional shape. So we can say then that h over r, or I'll just do r over h for this, either way, r over h of the water level equals 3 over 12 for the cup. Now I said that I wanted to replace the r's with h's. So that means that I'm going to have to isolate r over here so that I can substitute something in for it in this volume equation. So if I multiply both sides by h and reduce, I can write r equals h over 4. Okay, now that I can express the radius with height instead, I'm going to go ahead and replace this r with that h over 4. And let's clean this up and simplify a little bit. So this is going to be h squared over 16. That's going to give me an h cubed, and 1/3 times 1/16 is 1 over 48, which we can put a pi on top of. So pi over 48 h cubed, that is our simplified volume formula. It's time to differentiate. So on the left side, we've got dv over dt. On the right side, we've got 3 over 48, which we reduced to 1 over 16, pi h squared, and then we'll have a dh over dt. At this point, let me plug in all the information they gave me. dv over dt, we know that that's 2. That's the rate of change of the volume. And then we know that h, they told us that the cup had a water level of 5 centimeters. So plug in those things in. Let's see if I can solve now for dh over dt. This was a calculator question. However, if you look at the answer choices, these do not look like answer choices that got plugged into a calculator. Let's just see if we can do this without one. So multiply both sides by 16, that's 32. Divide by 25 pi, we've got 32 over 25 pi centimeters per second, which matches answer choice A. On this problem, we have positive variables p and c that change with respect to time, and their relationship is given by this equation right here. At the instant when dp over dt is 41 and c is 15, they want the value of dc over dt. So in order to get all of these different quantities in one place, we've had to start with this equation here and then implicitly differentiate it with respect to time. This is a related rates problem. To get the related rates, we need the derivatives. So starting on the left, derivative of p squared, that's going to be 2p, and we have a tail of dp over dt, because we're differentiating again with respect to time. On the right side, we're going to need a chain rule on this one. So we have 3 times 20 minus c quantity squared times, now we have to take the derivative of the stuff inside here. So we have a negative c, so that's going to be a negative 1 times dc over dt. All right, everything's in one place. At this point, it's time to fill in everything except dc over dt, because that's what we're trying to solve for. So do we know what p is? We actually do not. They never told us p. So we're going to have to find p. Do we know dp over dt? We do. It's 41. We also know c is 15. So it's just p that we have to find. Once we find that, we can plug it in with those other things and solve for dc over dt. So to solve for p, we're going to go back to the original equation up here. P squared equals 20 minus c to the third power. Because again, we know what c is. So all you need to know to find p is to know what c is, plug it in, and solve for p. So doing that, we've got p squared equals 20 minus 15 cubed. So that means p squared equals, let's see, this is 5 cubed, so 125. And then the square root of 125, and we know it's not plus or minus because they said positive variables p and c. The square root of 125, that's going to be 5 radical 5 if you simplify the radical. And we're going to simplify the radical because it's no calculator problem, and all the answer choices have radical 5s with them anyway. So now that we've got p, let's plug that in along with the c value 15 and dp over dt 41 to this mess over here. So we have 2 times 5 root 5 times 41 equals 3 times 20 minus 15 times negative 1 dc dt. And I put the negative out here with the 3 just so I don't have to keep carrying it around. So how can we simplify this mess and solve for dc over dt? Well, essentially we have to divide by all of this stuff that is not dc over dt. So I'm going to move all that stuff down here, and I'm going to simplify a little bit. This is really 5 squared, so 25 times negative 3. Put that down here. And let's see here. We're actually not too far away. This looks like a big mess, but if you look at the answer choices, they're kind of messy too. So let's see what we can do here. 5 and 25, that can reduce a little bit. So that gives us negative 3 times 5 down here. That's going to be negative 15 in the denominator. Upstairs, we have 2 times 41, which is 82, and there's still a radical 5 left over. So when the dust settles then, we have 82 root 5 over 15, all negative, giving us answer choice D.